Hi, everyone. Thank you for joining us. So today we are going to present to you one of our latest investigation about perhaps the most interesting backdoor that we've ever investigated, called Squidoor. This presentation will not be just around a very interesting story, but it will be practical. We'll share our insights and our hunting methodology and explore our investigation process step by step. So before we begin, let us quickly introduce ourselves. So my name is Lior. I'm a senior researcher at Palo Alto Networks. And today with me is Tom Fakterman. Tom, say hi.
Hello, everyone. I'm a senior SAT researcher. I'm working with Lior in the Cortex Threat Research team.
Great. So now we can begin. So today we're going to share with you this really interesting story about this new backdoor that we discovered called Squidoor. We'll start this presentation with some background about how it all started and what we were initially hunting for. Then we'll dive into the activity itself and talk about the attack flow and the main TTPs that we observed. Later on, Tom will walk us through the Squidoor backdoor itself, its command and control methods, capabilities, and how it was used in the attacks. Once we have some understanding of the Squidoor backdoor and the attack flow, we will share how we can actually catch a Squidoor. And we'll finish off with some key takeaways. Since we have a pretty packed agenda today, I wanted to first set the stage and provide you with some context about this investigation. So what we uncovered is a suspected Chinese threat actor that has been active since at least March of 2023, primarily targeting two main regions, Southeast Asia and South America, and focusing on very high-profile organizations, such as governments, defense, telecommunication, aviation, and education sectors. And here's what this is why this investigation is so interesting. The backdoor that was used is Squidoor, a multi-platform modular backdoor that supports no less than 10 different command and control methods, making it exceptionally difficult to detect and block. But how it all started, how we did even find these things. So let's go back to the beginning. So one of our main tasks as a team is to conduct hunting across our telemetry and search for both known threats and hidden attacks that haven't been reported before. We find it very crucial to have this proactive hunting approach if we want to find and search for these sophisticated adversaries. And what we basically do is we monitor the global threat landscape, and we basically organize our work around different hunting leads or hunting projects. And this really helps us to understand where we need to focus our efforts. And one of those hunting projects that we had focused on IIS exploitations. As I'm sure all of you know, IIS servers are particularly vulnerable to attacks. Since 2021, we have seen a surge of different vulnerabilities that made these servers extremely attractive targets for both cybercrimes and nation-state threat actors. What makes IIS servers especially concerning is that many of the exploits do not require any type of authentication or credentials in order to execute. An attacker can just gain access without needing to steal or to crack passwords first. And to make matters even worse, despite the known risks, many IIS servers across organizations still remain unpatched, creating a perfect storm of security gaps that adversaries are actively exploiting. And now let's see some examples of how we perform this hunting. First, we look for suspicious process trees under W3WP, the IIS worker process. A pattern that we watch for is something like W3WP, spawning some sort of a shell, for example, cmd.exe, that spawns suspicious commands, such as reconnaissance commands. And this type of activity usually indicates an attacker has gained access and is now trying to understand the network topology. Another thing that we monitor is file creation by W3WP, and specifically at high-risk locations, such as www.root and different temporary folders. And this usually indicates an attacker trying to deliver additional payloads through a web shell. And another critical technique that we monitor is process injection, where W3WP injects code into another process through DLL injection, process hollowing, and also direct shellcode execution. And these hunting techniques have been proven effective at identifying and hunting for IS exploitation attempts. And to get this information, we leverage different data sources, such as EDR solutions, Windows event logs, IIS logs, Sysmon rules, and Yara rules that were specifically designed to detect web shells. After we crafted those hunting queries, we ran them across our telemetry and examined the results. One particular interesting incident really caught our attention. It was a potential compromise of a defense infrastructure in Southeast Asia. This, of course, was very concerning to us, especially given the sensitive nature of defense organizations and the strategic importance of this region. Of course, we immediately began the investigation. And let's talk about what we actually found. Let's examine the attack flow and explore some of the main TTPs. Since we started this investigation hunting for IS exploitation attempts, it's no surprise that the initial access vector was through an IS server in the organization. But it was not that straightforward. Our investigation revealed that the threat actor actually attempted to exploit multiple IS servers in the environment. Fortunately, most of these servers were already patched, so they successfully resisted the attack. However, our threat actor demonstrated remarkable determination, where they methodically worked their way through the organization infrastructure, testing for different vulnerabilities on multiple entry points. Eventually, their persistence paid off when they discovered a single unpatched IS server. This single server that missed the patch cycle was all they needed to gain access and to deploy the web shell that you see on the screen. And once they got access to the environment, the threat actor immediately began expanding their presence. Our telemetry revealed that the threat actor methodically worked the way to ensure that they have multiple entry points to the environment by spreading their web shells across other IIS and web servers. The lateral movement followed a pretty clear progression strategy. First, the threat actor downloaded their primary web shell from an external bash upload service. Then they renamed those web shells and saved them under different file names. And to hide their malicious activity, they employed a pretty clever technique. They tried to masquerade those web shells as legitimate certificate files before copying them remotely to other servers. And finally, they utilized curl commands to deploy those web shells on the newly targeted servers. And these propagation methods showed the threat actor sophistication and also their persistence by ensuring that even if one entry point was discovered and removed, multiple others would remain available. And while we were examining and investigating the different web shells that we found, a piece of forensic evidence emerged that kind of gave us an initial lead about the potential origin of our threat actor. The following ASPX header represents an HTTP request to one of the deployed web shells called error.aspx. An ASPX header is the opening section of an ASP.NET web page that basically contains instructions how the servers should process the page. And particularly notable in this request is the accept language field, which lists ZHCN as the primary language preference. This indicates that the threat actor's machine was actually configured with simplified Chinese. And initially, that points us toward a Chinese-speaking threat actor. And of course, it was very interesting for us and also very concerning, especially given the target sector and region. And after the threat actor spread across the environment, they executed a chain of events that really caught our attention. We found out that they executed this really suspicious file called font.drvhost.exe with this unusual parameter, a config.ini file. This immediately raised red flag to us. Our investigation revealed that this file was actually not the legitimate Windows font driver host at all, but it was actually a renamed cdb.exe, a Windows debugging utility. And this utility is actually listed as a living of the land binary, or lolbus, since it can be abused to load shellcodes in memory. And our threat actor used this disguised utility to load a malicious shellcode from this config.ini file that we saw. The shellcode actually contained a malicious binary inside, and when executed, it loads it in memory. When we investigated this DLL that was reflectively loaded, we actually found out that it's new and undocumented malware, which we named Squidoor. And now I'll pass the stage to Tom to dive a bit deeper into the Squidoor backdoor itself, talk about some of its capabilities, command and control methods, and how it was actually used in the attack.
Thank you, Lior. So as Lior mentioned, as part of our investigation, we found this unknown malware, which we eventually dubbed Squidoor. We found versions of the Squidoor malware for both the Windows and Linux systems. But the big picture is that this malware basically gives the attackers full control over the infected machine. It gives them capabilities like collecting information about the infected host, executing commands, manipulating files, and a lot of other malicious capabilities it enables them to do. But the really interesting part, and what makes this malware so unique, is how it communicates with the command and control. Or to be more specific, in how many ways it can communicate with the command and control. Squidoor is able to use 10 different methods to communicate with the attackers on the Windows version and 9 different methods on the Linux version. We can see here some straightforward methods like HTTP, reverse TCP, reverse UDP. It can use some more stealthy methods like DNS tunneling or ICMP tunneling, and also some rare and unique methods like using the Outlook mail client API to send and receive commands from the attackers. Being able to use so many different methods for communication makes Squidoor a very powerful malware. And that is because it enables the attackers to create some sort of a net of Squidoors inside an infected network. We created here an illustration of one of the infected environments we investigated. And inside that environment, we saw a bunch of different Squidoor implants who were communicating internally with each other. And some of them were using different protocols for communication. Some are using SMB, some are using TCP, some are using ICMP to communicate. But only a very few Squidoor implants were actually used for external communication outside of the network. And for that, they used protocols like HTTP and the Outlook mail client API. Now, this approach is very stealthy, as even though the network is filled with malware, actual malicious communication outside of the environment is very limited. And we will soon explore how the attackers are able to use the Outlook mail client API. And we will understand that whatever malicious communication that does actually go out of the environment goes over completely legitimate services, which makes it very hard to detect. So I want to explore how the attackers are able to abuse Outlook in order to send and receive commands for Squidoor. And this process is a bit complicated, so we divided it into 3 main stages. In the first stage, Squidoor will need to log in into the Microsoft Identity Platform. In the second stage, Squidoor will send a unique identifier to the attackers. And in the last stage, Squidoor will receive commands to execute. So now let's deep dive and explore how each stage works. Of course, we start with the first one. So Squidoor needs to log in into the Microsoft Identity Platform. And to do that, it will use a hard-coded refresh token, which is saved inside Squidoor's hard-coded encrypted configuration. After Squidoor logs in, it will need to send a unique identifier to the attackers. And this is how this process works. Squidoor will use the Outlook REST API to query the draft email folder of the attackers for an email with a very specific subject. The subject starts with the letter P underscore, and after that, some random generated number. This generated number is basically a unique identifier for that specific Squidoor instance. So by using a unique identifier for each Squidoor instance, the attackers are able to utilize only a single Outlook mailbox to control several different Squidoor implants in the same network, or even on different networks. Now, if this is the first time that Squidoor is trying to find this email, it will probably not find it yet, So it will create in a new one and will send it to the attackers. It will create its own unique identifier. And the content of the email will be some random sequence of bytes which are encoded in base 64. Once the attackers receive this email, it is a sign for them that a new Squidoor implant has connected to their mailbox and is now listening for commands. So Squidoor needs to receive those commands to execute. And this is how it does it. In a very similar manner, Squidoor will use the Alto REST API to query the attacker's draft folder for an email with a very specific subject. This time, it starts with the letter R underscore, and then again the same unique identifier. And Squidoor will keep searching for this email in a loop until it will finally find one. This is the exact query that Squidoor is using to try and find this email in the attacker's mailbox. Once the attackers decide to finally send commands to Squidoor and create the email, Squidoor will retrieve the mail content from the attacker's mailbox and delete the mail from the attacker's mailbox. So this whole intricate process is how the attackers are able to abuse Outlook in order to function as a command and control and send commands to their malware. Now, when Squidoor retrieves this email that contains the commands, the email content is actually encrypted in several layers of encoding and encryption. And this is the decryption flow that Squidoor is using. The first layer is encoded via base 64. The second layer is decrypted via a combination of AES algorithm and a custom XOR decryption algorithm. And the last layer is decompressed via zlib. And after all of that process, what we get at the end is either commands to execute or additional modules for Squidoor to execute and load. As part of our investigation, we saw the attackers deliver a lot of different additional modules for Squidoor. They use the modules to execute different PowerShell scripts, to perform pass-the-hash attacks, to load and execute shellcode. The modules help them for network and user enumeration inside the victim environments, and also to upload files to remote machines. In the image here, you can see how the attackers use the different modules as part of the attack. Each module was injected into a different instance of mspaint.exe process. And each module needs a unique password in order to execute. This is what you see in the blue rectangle. Now, these passwords also function as a great sandbox evasion technique. Because if we now upload these modules into a sandbox without the password, it will probably not execute right. And it's also a great hindrance for malware analysts, as now we need to reverse engineer the module to understand what is the correct password so we can actually use it. And again, you can see how the attackers actually use the passwords. Some examples were to create persistence on remote machines, to execute reconnaissance commands. And we also saw them using it to search for users of specific individuals who worked for the victim organizations. There is one last aspect of Squidoor that I want to highlight. Inside Squidoor's configuration, we found a Pastebin URL. And what we saw is that as part of its execution, Squidoor sent a HTTP GET request to that Pastebin URL and retrieved the content, which was only the number 1. And after that, it did absolutely nothing with it. So that made us really curious. Why was Squidoor retrieving this specific Pastebin page? What was it doing with it? So we decided to dig deeper and see what else was on this Pastebin account. And inside, we found a bunch of additional access tokens and API keys for a lot of different services. So it looks like the attackers used this Pastebin page to store some data for their attacks. Now, as part of our investigation, we continued to track the activity on this Pastebin page. And one day, everything inside the Pastebin page has changed. As you can see here, some of the back files are censored. And that is because they contain names of different government organizations who are potentially infected with the Squidoor malware. So it looks like now the attackers used Pastebin to store some information about potential victims. As part of our research publication, we shared the images that I just showed you. And like a day after we published our research, this account was completely removed and deleted from Pastebin. So it looks like the attackers really hurried to hide their footprints from Pastebin once they realized that someone was onto them. But what we actually realized is that they just switched to use a different Pastebin account, which we also had access to from analyzing other Squidoor implants. So we could use the other Pastebin accounts to continue to track the activities of the threat actor and the activities of Squidoor. So now that we understand how the Squidoor malware works and the little intricacies behind how it operates, I will pass the stage to Lior again to tell you how we can catch a Squidoor.
Thank you, Tom. So before diving into the Squidoor hunting process itself, let's first examine our intelligence-driven hunting methodology in at least a few sentences. So what is intelligence-driven hunting? Intelligence-driven hunting is a complementary approach to generic threat hunting, and it's very threat-centric. It's more accurate, but of course more time-consuming and more expensive. We use it if we want to hunt for threats that are relevant to a specific organization, industry, or even a specific region. Intelligence-driven hunting also provides us with the much-needed context. It can help us distinguish between one evil from another, help us with the attribution process and severity, prioritization, to know which threat we should handle first. And it's very helpful when it comes to tracking threat actors and also understanding their victimology pattern. Let's get practical. What does intelligence-driven hunting actually produce? So every investigation that we conduct and every report we read becomes a source of actionable intelligence. We are constantly extracting specific elements that help us to track these threat actors and to hunt for similar activities. First, we look at the generic TTPs. These are everything from the threat actors' preferred exploits to their methods of operations, activity patterns, and even file naming conventions. These behavioral patterns usually persist even if malware changes. And of course, we also collect the traditional IOCs, or as we like to call them, low-hanging fruits. These are everything from the domains, the IPs, certificates, file hashes, and basically everything that provides us with immediate detection capabilities. We also create Yara rules for the custom malware and the payloads that we encounter. And these Yara rules actually becomes a very powerful tools that help us to identify even a slightly modified version of the same malware. In addition, we keep track of indicative command line arguments, those unusual command lines or unique parameter combinations that threat actors like to use. And surprisingly useful are the username and passwords created by threat actors. From our experience, threat actors are kind of a creature of habits, and they frequently reuse their username and passwords pattern across different campaigns. Now let's see this actionable intelligence in work. So this approach not only helped us to discover additional payloads related to the attack, but also gave us crucial insights into the threat actor's victimology pattern and the scope of their operation. And I'm sure all of you are familiar with VirusTotal and even use it. We use it quite a lot when it comes to sample searching and pivoting, and this investigation was no exception. As you may remember, our investigation started with this key observation. The threat actor had renamed the utility cdb.exe to fontdrvhost.exe. We wanted to know how common this practice is, and to see if maybe similar files were submitted to VirusTotal. After searching for this specific combination, we actually found only one result. And the file matches the file hash that we found in our investigation. And since cdb.exe is a legitimate Windows binary, it naturally had numerous submitters. However, two submitters caught our attention, since they submitted it by the name fontdrvhost.exe rather than cdb.exe, like the rest. One submitter was from Singapore and another from Brazil. We of course wanted to know what else those submitters uploaded to VT that may be related to the attack. While pivoting on a specific submitter is not a standard VirusTotal feature, we still find a way to do it anyway. What we did is searching for submissions from Singapore within a specific date range of the same time of the submission of the PhoneDRV host file. And we also filtered for web submissions rather than API submissions. You can see the exact search on the screen. And this search returned approximately 200 files. Among them, we spotted a pretty familiar file, a file named config.ini that was submitted by the same user on the same day. And this file turned out to be, well, you guessed it, an encrypted shellcode containing the Squidoor payload. Of course, we repeated the process with the other submission, the Brazilian one, and we found another Squidoor payload. And by the way, both of them had 0 detection hits when we first discovered them. And this was only one method to hunt for Squidoor binaries in VT. Let's explore another one. This time by leveraging VirusTotal live hunt feature. So we created custom Yara rules that were based on something very indicative for Squidoor. It's command and control methods. What made this a bit straightforward is that Squidoor supports 10 different command control methods, and they are all clearly listed in the code, right, as you can see on the screen. And this made the creation of effective Yara rules for Squidoor relatively simple. And after we deployed these rules, we waited to see if we get any results, if new samples will be submitted to VT. And after a few days, we actually got a result. This search uncovered an ELF version of the malware, revealing something very important that we hadn't known before. Squidoor actually exists in 2 versions, one targeting Windows systems and another designed for Linux environments. And besides our VirusTotal discoveries, we also identified several effective ways to hunt for Squidoor activity in the network. The first methods involved Squidoor Outlook communication methods. We found it effective looking for non-browser processes that communicates with both graphmicrosoft.com and Pastebin. This unique combination is a strong indicator for Squidoor activity. We also identified a unique URI pattern in the network traffic. Looking for GET requests that contains the parameters that you see on the screen is also a very good indicator for Squidoor presence, since those patterns appears when the malware actually queries for command emails. And these hunting techniques really shows and demonstrate how information and intelligence gathered from initial discoveries can be transformed into practical hunting methods across different security layers. And after we crafted those hunting queries, we ran them across our telemetry. And soon after that, we noticed that we have additional potential victims that we were initially not aware of. What immediately stood out to us was the geographic pattern. While Southeast Asia was already known to us as a targeted region, our investigation revealed South America as yet another significant focus area of this threat actor. And as for the sectors being targeted, we found a pretty clear pattern. This threat actor targets very high-profile organizations such as governments, defense, telecommunication, aviation, and education sectors. And these are not random targets. These are high-value organizations that have access to very sensitive information, revealing that this is a carefully planned attack with very specific intelligence goals. And this broader picture really helped us to know the threat actors through priorities, show us exactly who they were targeting, and help us to understand the scope of the operation. And now after we have some understanding of the attack and even familiar with Squidoor, and also know how to catch one, I will pass the stage to Tom one last time to share with you our key takeaways.
Thank you, Lior. So in this session, we talked about how the Squidoor malware works and how the attackers got access to the environments. We discussed how we can hunt for Squidoors in VirusTotal and in our networks. But after all of that, these are the main 3 points we really want you to take from this session. So the first point is that threat actors only require a single unprotected asset in order to gain access. And I know it might sound obvious at this point. You need to patch your systems. But take as an example the victim we discussed at the start of our session. Most of their servers were indeed patched. But of course, it was Murphy's Law, and the attackers managed to find that single unpatched servers, which they used to gain access and start a full-fledged attack. So this is why we highlight this point, that it is important to make sure that all your systems are fully patched. The second point we want you to remember, that threat actors can and will try to hide in plain sight. Squidoor is using completely legitimate services like Outlook in order to mask its communication with the attackers and command and control. And we also discussed how the attackers used Pastebin, a legitimate site, in order to store data about the attack and the victims. So this very stealthy approach of hiding in plain sight makes traditional security monitoring a lot more challenging. And the last point we want to highlight is the importance of intelligence-driven hunting. By carefully analyzing and understanding the TTPs of the attacker, we were able to create relevant hunting queries and actionable intelligence, which in turn helped us to find more victims and also discover other versions of the Squidoor malware. So this is why we always recommend to include intelligence-driven hunting as part of our day-to-day hunting efforts. Thank you so much, everybody, for listening to us today. We had a great time. And if we still have some time for questions, we'll be happy to take any.
Thank you.